Hi everybody, this is Grisha Chandy from Molecular Devices. Welcome to our webinar series. Today we're going to be talking about multiplexed high-content hepatotoxicity assays using iPSC-Derived hepatocytes. Okay. Thank you very much for joining. The agenda is I'll give you a short introduction to what's new with Molecular Devices APS products. I'm the product manager for cellular imaging at Molecular Devices. And then Vanessa Ott from Cellular Dynamics International will give an introduction to iPSC-Derived hepatocytes. And the bulk of the talk will be from a research scientist with Molecular Devices, Oksana Franco, who's going to go through some examples of using these cells for with high-content screening and even a short proof of principle screen we've done. Some housekeeping. If you need help with the WebEx, you're not seeing these slides or there's problems with the audio, there's a phone number, 1-866-229-3239, or you can send questions by the Q&A window, which I'm going to show you how to do right now. So you can press on the Q&A button on the toolbar at the top to expand the Q&A window. Click on the Q&A. You'll get a window where you can type your question. And please choose all panelists when you send the question to us so that we can all of us online can see and respond to your question. So type in the question, choose all panelists, press the send button. Okay. So a short introduction to the high-content screening workflow for those unfamiliar with high-content screening. There's usually some driver to acquire cells in a plate or slide format to do some type of screen. And you need to acquire images across the plate. Okay, acquire those images. You need to convert those images to numerical values. You need to do some type of image analysis. You need to convert those numbers to some meaningful data analysis. And there needs to be some storage and management of that data in an integrated fashion because the amount of data you're collecting is quite large. There are many applications that are enabled with high-content screening. I showed just some examples here. Top left is a high resolution receptor endocytosis where you're counting the number of dots that show up within a cell. Angiogenesis and some type of spheroid analysis would be sort of a more low resolution, bigger object imaging. Urite outgrowth is a very popular assay to look at neural diseases or neural phenotypes. And micronuclei formation is again another high-resolution genotoxicity assay that one might expect to run. The Molecular Devices imaging solutions are shown on this slide. At the top left, you have the Image Express Micro, which the data that Oksana is going to present were collected with. Additionally, you have the Image Express Ultra system, which is a confocal screening device. Okay. You can bring third-party images into our back-end. You can also bring third-party images into our back-end data management solution, MDC Store. So you have the Image Express Micro, the Ultra, and third-party images that can be brought into the data management system. As I mentioned, Oksana is going to be speaking about the Micro. On the top right, you also have our analysis software, which is MedExpress, and MedExpress PowerCore that allows turning those images into numerical values and looking at those numerical values. And hit selection is done with the QtExpress software to do your data analytics. New is this ability to bring images from third-party imaging systems into MDC Store. And new is some features of MedExpress that increase the application space that can be that makes it amenable for high content, high throughput screening. Okay. We've had the ImageXpress Micro XL system on the market for a little over a year, but so it's somewhat new. Just to remind people that most standard imaging systems would have a smaller field of view, which is depicted on the left, and this is the green box is the field of view of a standard imaging APS system on a representative on a size 384-well plate. So the 4x objective with the XL system, you can capture one image to capture the whole well. If you want to go to, and this drives 3 times the number of objects in a single field of view, or if you're going for larger, high resolution images, it allows less images to be acquired for those larger objects. It also comes with a solid state light source, which allows for on-demand illumination. There's no mechanical shutter, and that's reducing support requirements. Here is sort of that field of view shown with some neuronal assays. Standard system, you'd have to collect a large number. You'd get about 120 cells counted in that image. We've validated assays with a standard system, and you see the Z prime and the assay window there. And you have to collect a large number of images to get most of that well. On the right is the ImageXpress XL image, where you have a much larger field of view. You're collecting much more than 3 times the number of cells. Your assay window is improved because of the larger number of objects you're counting. If you needed to collect a large fraction of the well, you'd have to collect much fewer images. And the speed of the system is quite fast. Here with a single image, 2x binning, 96-well plate, you would be able to acquire this plate in less than 4 minutes. New also to MetaXpress is our custom module editor, which now allows for you to develop custom analysis in one location. This tool comes to us from Metamorph NX, and what you're seeing here is the ability to identify your objects, create this with number of step cards, and seeing the steps that you're doing through image processing on the bottom right, and your mask is shown all in one window. Okay. Here is an example. So this allows for many more assays to be developed beyond the standard modules. Here's one with membrane intensity module that we created as a proof that you can do that, and the yellow outline is that of the membrane, and the dark blue is the nuclei, and the light blue is the cytosol. Once it's generated, it will be able to be reused and shared. Whether this module is created in Metamorph or MetaXpress, it can be shared with your colleagues or shared between your assay development group and an APS system. Another one is being able to measure objects inside compartments. Just to show as an example, maybe you want to count these small dots on the length of a neurite, and here it is these little pink objects which you may not be able to see, but I show you in a blow up where these little yellow dots, you want to count those on these neurites. Here I show 3 examples of them, and here they show up as pink masks on top of the neurites. But Oksana and Vanessa are going to talk to you about hepatocytes and about the ability to make multiple measurements on these cells. So here's an example of the ability to multiplex many outputs from a single module. This is an image of a mask of a confluent hepatocyte, where you can flag whether the cells are positive for some intensity or shape. So here the yellow areas is they're positive where the green dye was dye was not located. Blue is where all of the green dye was located. Sorry for the typo. Purple is where there may have been a mitotracker objects. Pink are non-apoptotic nuclei. White might be apoptotic nuclei, and another light blue where the cytoplasm was negative for some threshold of intensity. So you can collect quite a number of different parameters from a single module. Okay. Now what's very nice about the custom module editor with MetaXpress is once you've created a module, not only is it available to be shared, but you can run through MetaXpress Calc or MedExpress PowerCore is an option on MedExpress that allows the bringing on of a number of computer cores or computer processors to run an analysis in parallel. And you can drive your analysis time to be faster than acquisition this way. And rather than taking many minutes or many hours for a complex analysis, your image analysis can be done in minutes. So example applications now can be accelerated. I mentioned membrane analysis, puncture analysis on compartments. It can be within nuclei, inside membranes, on neurites, co-localization assays, label-free cell proliferation can be done now with the custom module editor, wound healing assays, scratch or platypus. Parametric staining is now enabled, and most morphometry shape measurements. Okay, I think Oksana has some nice data to show on that. Images micro Excel system now with MedExpress 5 software should alleviate your day-to-day challenges. You can run more screens because of the speed improvement, as well as the increased application space that's amenable to high throughput. Allows you to perform hit selection quickly. You have a reliable product for maximum uptime. Your image quality is maintained, and now you can definitely grow with your expanding applications. For more information, please go to hightroughputimaging.com. So at this time, I'd like to hand this over to Vanessa, who's going to give you a short introduction to iPSC-derived hepatocytes. Vanessa?
Okay. Thank you very much. I'm going to go ahead and pull up the slides. So, by way of introduction, the story that Oksana is going to tell today, showing the use of iPS-derived hepatocytes and the ImageExpress platform, is really aimed to begin to address a very important problem in drug development, and that's drug-induced liver toxicity. So as most everybody is probably aware, drug-induced liver injury is associated with a very high percentage, greater than 33% of acute liver failures in the United States. And there are roughly 1,000 drugs that have been implicated in causing liver disease. Some of the more known drugs are shown here on this slide and result in liver diseases ranging from acute and chronic hepatitis to hepatocarcinoma. Importantly, drug-induced liver injury is often not evident in preclinical and clinical studies. So shown on this slide is an overview of current hepatocyte model systems that are in use today. So the gold standard is primary human hepatocytes, which are available as either fresh or cryopreserved cells. These have a number of limitations, including availability, phenotypic instability once the cells are placed in cultures, and importantly, unpredictable donor variability. In addition, there's really limited genotypic information for these cells. In addition, there are a number of cell lines that are widely used to evaluate hepatotoxicity. These include HepG2 cells, HepA-RG cells, but like most transformed cell lines, they lack a number of key functions to recapitulate normal human biology. In the case of HepG2 cells, they're known for lacking some of the key metabolic enzyme functions. In addition, these cell lines do not represent individual diversity in a population. And in some cases, there's some significant lot-to-lot variability that needs to be addressed and taken into consideration when using these cell lines. And of course, animal models are widely used, but have the limitations of species differences and being able to extend the study of an animal model to human outcomes. The use of animal models is resource intensive, with a lot of time and cost put into using these models. And really, there's limited power to predict idiosyncratic events. And then, of course, there's probably globally a move to try to reduce the number of animals used in such testing. So there's a lot of interest to explore the use of iPS cell technology to develop cellular models to overcome a lot of these limitations. So at Cellular Dynamics, we're really focused on bringing to market terminally differentiated cells for use in drug development that are derived from iPS cells. So iPS cells, or induced pluripotent stem cells, are uniquely useful stem cells. They're derived from adult tissue via relatively non-invasive methods. They can be expanded indefinitely, differentiated into any cell type in the body, and fully pluripotent. The iPS cells offer distinct advantages compared to ES cells. They can be created via relatively streamlined and non-invasive methods. They eliminate many of the political and social issues regarding tissue source. And probably most importantly from a scientific perspective is that it really enables modeling of diversity of genotype and phenotype within a population. So this last point is further illustrated on this slide, and it attempts to show the real revolutionary access that this technology provides to human biology. So as I mentioned, the iPS cells can be used to differentiate all 208 cell types in the human body, in theory. iPS cells can be created from any individual. And then, more recently, as technologies for genome editing or genetic engineering in iPS cells has evolved, we now have the opportunity to use iPS cells and go in and edit any genome in the genome, or any gene in the genome. So really, as we look at this technology, we see a real potential to revolutionize life science research. But this requires expertise in reprogramming terminally differentiated cells into iPS cells, reprogramming differentiation, and also genetic engineering. And genetic engineering, for example, can be used to introduce a specific genotype, to correct a disease mutation, or even to engineer reporter assays for high-throughput screening types of applications. So this is a focus for what we're doing at CDI, is to really bring together all of these capabilities to really move forward the technology to its fullest potential. So as we think about in vitro model systems, we think a lot about what are the ideal or necessary characteristics of these model systems. And these include quality, so the model system needs to exhibit key cellular characteristics, recapitulate normal human biology, be reproducible, and provide a known and relevant genotype. In addition, it's important that these model systems consist of cell types that are highly pure. So we use a variety of methods, which I won't go into detail in this presentation, to achieve very high purity when we manufacture terminal cell types. So all of the cell types that we manufacture, including the hepatocytes, which you'll hear about today, are greater than 95% pure. And importantly, this purity is maintained over time in culture. And then finally, quantity. And this is a critical for really bringing the technology into mainstream use. And it really needs to be enough at commercial scale to support high throughput drug screening and safety testing. And as one example, we're currently producing hepatocytes at a rate of over 1 billion cells per week. And the process that we use to manufacture hepatocytes is completely scalable, so we can increase that very easily as the use and the demand for the cell type evolves. So the next few slides will show you some basic characterization data of the hepatocyte. So this slide shows the typical hepatocyte morphology. These cells were plated, and this image was taken about 24 to 48 hours post-plating. And you can see that the cells form an adherent monolayer. They have a good nuclear morphology. The areas on the slide that are circled show places in the culture where you see evidence of binucleation, which is a sign of cell maturity. In addition, the arrows are pointing to some regions here in this phase image that indicate the formation of functional biocanaliculli, and I'll show you some additional data to that point in a couple of slides. This slide shows some examples of protein expression, so typical hepatocyte markers, which include alpha-1 antitrypsin and albumin, which are indicated both in red, and you can see the robust cytoplasmic staining of these two proteins. On the upper right shows nuclear expression of the HNF4 alpha transcription factor. And on the lower right is a dual stain with a blue nuclear stain and the green indicating expression of occlutin, which is an important tight junction protein expressed in hepatocytes and also one receptor for the HCV virus. This slide shows some additional examples of morphology, and specifically on the left, it shows what the morphology looks like over time post-plating. So you can see that the cells really sit down and form a monolayer as quickly as 2 hours post-plating. After plating, we recommend immediate change after 4 hours to get rid of some of the dead cells on the top of the culture. And then you can see that you get probably better spreading out and a more tight monolayer after the first day, which is maintained for several days in culture. And you can see here the large images are taken 4 days post-plating, and the lower left is CD-FDA staining, which is another marker for the formation of functional biochanneliculi. In terms of length of time in culture, I'm showing this slide. This was data generated by one of our pharmaceutical partners at Roche, and what they did in this experiment was they plated the iCell hepatocytes and maintained those cultures out 21 days in culture. We have a fair amount of data over this period of time. We also have carried some cultures here at CDI out to roughly 40 or 50 days with and seeing the maintenance of that morphology. In contrast, you can see with primary human hepatocytes that you rapidly lose this morphology, actually within probably about the first week post-plating. This slide shows some basic intrinsic functions of the hepatocytes, which include albumin production in the upper left, which is indicated by ELISA. On the upper right is glycogen storage, measured by periodic acid shift staining, and the bottom two images show lipid storage measured by both oil red and the Bo-Dippy dye staining. So the next two slides are some basic characterization of hepatotoxic responses. These data were generated in collaboration with Promega, and what you can see here is a study that we did using the cell titer glow cell liability assay from Promega, and you can see that the cells lose viability in an anticipated manner in response to triglycerides, terfenadine, tamoxifen, and chlorpromazine. In contrast, the cells did not lose viability in response to theophylline, which is an expected negative control. And with acetaminophen, you start to see toxicity at higher doses, which is, again, consistent with what you would expect. This is an interesting slide and a small case study that we also did in collaboration with Promega. And here the iCell hepatocytes, which are shown in the left by the red line, the iCell hepatocytes lose viability in response to aflatoxin, similar to primary human hepatocytes. And this is significant because aflatoxin is actually the toxicity in response to aflatoxin requires the formation of a metabolic intermediate. So in this case, the hepatotoxicity is due to the formation of a metabolic intermediate, which indicates that these cells are metabolically active. In contrast, you don't see any loss of viability in the HepG2 cells. Again, as I mentioned earlier, the HepG2 cells are notorious for having low or no metabolic activity. So further supporting these data, in this experiment, the toxicity in the iCell hepatocytes was inhibited when the cells were treated with ketoconazole and alpha-nasoflavone, which are inhibitors of P450 enzymes. So in summary for this part of the presentation, just to recap that the hepatocytes are terminally differentiated, non-proliferating cells derived from human iPS cells. We have a known genotype, so we know all the different polymorphisms of the various hepatocyte specific genes. The cells are greater than 95% pure, slatable, and can be maintained for at least 3 weeks in culture. The cells exhibit a number of very useful and important hepatocyte characteristics and functions, and can be used to assess a variety of biochemical and cellular assays, a number of which are listed here on this slide. I'll in particular call out the last bullet point, which is the use of the cells for infectious disease studies, and we're finding very, very exciting applications for the cells in looking at hepatitis infectivity. So that's obviously beyond the scope of today's discussion, but feel free to contact me if you're interested to learn more about this or any of the other applications. So at this point, I'll turn it over to Oksana, who will go into much greater detail on multiplexed high-content hepatotoxicity assays using iPSL and the Image Express platform.
Hello, thank you so much, Vanessa, for a wonderful overview of such an interesting system as stem cell-derived hepatocytes. And I will be sharing with you some of our method development and data using high-content analysis for hepatotoxicity studies. So high-content analysis methods are well established for in vitro toxicity studies. They include cell count and nuclear characterization, as well as mitochondria integrity or oxidative stress. High-content analysis methods allow not only define the fact of toxicity, but also determine mode of action, whether it's apoptosis, necrosis, or mitochondrial damage. Multi-parametric readouts from each well allows minimized cell usage and also evaluate multiple mechanisms of toxicity. There's a number of publications on this topic, including O'Brien paper, which described using of HepG2 cells and hepatotoxicity studies in comparison morphological and biochemical readouts. Assay use multi-parametric analysis, which include nuclear shape, mitochondria potential, calcium content, and cell permeability. Some other publications being in this field using same or different cell model and also looking at multiplexed morphological and oxidative stress readouts. We are working on further development of high-content methods for hepatotoxicity application, and we've been using advanced cell model as stem cell-derived hepatocytes, which demonstrate functionality of mature liver cells. And also we developed robust multiplexed assay, which been optimized for 384-well format and includes multiple toxicity readouts. We took advantage from high-throughput imaging system, which has a large chip camera, which allows to capture 3 times greater cell number than a regular camera, which greatly improves throughput and also statistical analysis. Also, we have used the latest upgrade of Metamorph MetaExpress software, which includes custom module editor. This customized analysis algorithms allow to make tailored and optimized for multi-parametric outputs from different multiple toxicity readouts. Our multi-parametric cytotoxicity assays include cell viability markers like calcine AM, nuclear marker, HERS, and mitochondria integrity marker, MitoTracker Orange. I will describe in a little bit more detail our typical protocol. Cell hepatocytes plated on collagen plates in 384-well format. We usually use 12 to 15,000 cells per well. And in 48 hours, they apparent confluent and making good cell-to-cell junction. Those cells then treated with compounds for 72 hours in regular or galactose media. And then we use stain cells with mix of 3 dyes, like calcium, MitoTracker, and HERS for 60 minutes. Images acquired using 10x or 4x magnification, which allow to capture 2,000 cells or 8,000 to 10,000 cells per one site. We usually take one site per well and with 3 different colors. 50 tube for calcinium, 50 for MitoTracker Orange, and DAPI for HERS. Then we use customized image analysis, which includes multi-wavelength cell scoring, granularity, nuclear characterization, or includes customized special models. Here you can see enlarged image of cell hepatocytes, which have been cultured for several days, and stained with calcium, mitochondrial orange, and first. You can see viability stain calcium AM in green, orange mitochondria, and nuclear stain. When cells treated with toxic compound, you can observe dose-dependent decrease of number of cells expressing stain for calcium AM or mitochondria, and also decrease in intensity for those colors. Again, so each image allowed to capture a little bit over than 2,000 cells, and high resolution and advanced algorithms allow very efficient analysis and segmentation of confluent cell culture. So multi-parameter analysis using custom module editor. So here, 3 different stains could be processed simultaneously for different algorithms, whether it's nuclear characterization or cell scoring. So you can see here nuclear stain and calcium or mitochondria. Those cells could be analyzed and segmented in different steps, and not only allow count of different objects or cells, but also allow to define different parameter outcomes, like area, intensity, average or integrated, perimeter, or a number of other specialized outcomes. Custom algorithms could be used for general and specific toxicity, and it could be done in multiple steps, which include characterization of different stains, different markers, and subcellular organelles. Custom designed output parameters allow flexibility in toxicity outcomes, which allow quantitate cell scoring and define positive cell count, also total or average stain area, average or integrated intensity, nuclear characterization, cytoskeleton integrity, as well as granules, vesicles, or other internal objects. In this slide, you can see an example how a cell scoring was used to define number of calcium-positive cells. It could define also number of mitochondria-positive cells or positive cells for other markers, and also average or integrated intensity for different markers. These output parameters could be used to define IC50 for toxicity effects for different compounds. We usually take single site per well and cell segmented using nuclear stain. Calcium AM is apparently a very sensitive marker which has greater sensitivity for toxicity effects than just plain nuclear or cell count. We have compared IC50s defined by calcium AM as well as nuclear stain or mitochondria, mitotracker. So this kind of analysis shows that calcium AM apparently gives lower IC50 for different number of compounds, which suggests that it has higher sensitivity to the toxic effects than other markers. Cytoskeleton integrity is another interesting marker which could be done using Actin stain, using Alexa 488 palladium stain from in vitro gen. So you can see cytoskeleton stain with intact cells. So you can see nice junctions between different cells. But after treatment with toxin compounds like aflatoxin, you can see dose-dependent increase of actin intensity stain and also a decreased number of cells positive for actin. So number of actin-positive cells as well as actin average or integrated intensity could be used as output parameters to make IC50 dose-dependent curve. Actually, this parameter allows very good IC50 curves and works much better in dose responses than, for example, cell permeability dyes. In addition to such obvious parameters which react to toxicity, like number of viable cells, there are a number of other cell characteristics and morphological changes which are evident for cell biologists but more difficult to quantitate. For example, affected cells reject cell-to-cell contact and attachment with surface. So there could be not only pure cell number, but also changes in cell morphology. To quantitate for that, could be used other parameters such as total positive cell area. So it is apparently has greater sensitivity and dynamic range than just plain cell count. You can see some other example of this quantitation. For example, here cells treated with colchicine, you can see decreased cell number and also decreased area of stain for calcium AM. In another example, you can see cells treated with atorvastatin. In fact, the number of cells in this sample is about 20% lower than in a control, which doesn't make 3 standard deviations cut off. But when you look at area stained with calcium AM, you can see very significant changes, very significant decrease in this parameter, which is greater than 2-fold. So those subtle changes are actually very reproducible and statistically significant and provide additional information about toxicity. In this sample, you can see some very dramatic morphological changes caused by some toxic compounds. Some toxic compounds cause vascularization of cells and their ballooning and increase in cell area. Other compounds may change shrinking of cells and lose cell-to-cell contact, which results in decreased cell area. Those important changes in morphology could be quantitated by average stained cell area. Nuclear characterization is another very important marker for hepatotoxicity. In this example, you can see control cells, nuclear stain, and also cells treated with intermediate doses of taurosporin. Well, you can see very modest change in cell number. The change in a cell shape and morphology, nuclear morphology, is very dramatic. So apoptosis, which caused by taurosporin, results in nuclear condensation, which could be quantitated by decreased cell area and also increased average intensity. Those parameters could be characterized by software using nuclear count, cell sporing, or custom model algorithm. You can use nuclear area to build IC50s and define IC50s for different compounds and also to characterize apoptotic events. There is another example which you can see in enlarged images of nuclei of cells treated with different compounds. And those actually pretty subtle change are reproducible and statistically significant. So in addition to cell count and marker intensity, those parameters like characterization of cell area or nuclear shape are very important for defining hepatotoxicity and can be used as additional readout which provides additional information. I am going to describe several other hepatotoxicity assays which address specific types of hepatotoxicity, such as Mitochondria Potential, JC10 assay, phospholipidosis steatosis assay, or autophagy. Another endpoint also could be defined by the high-content analysis, include phosphate activation, inhibition of cell cycle, or DNA damage. Mitochondrial depolarization is an early signal for hypoxic damage or oxidative stress. This is a relatively short-term assay where cells treated with compounds for 30 to 90 minutes and then follow up by JC10 stain. So you can see in orange intact mitochondria which stained with the dye. But then cells which treated with antimycin A, which inhibitor of oxidation, so you can see that membranes of mitochondria lose their potential and dye is leaking into cytosol, which turns green. So you can analyze those changes using granularity model. granularity model allows characterization and masking of those different granules and allows quantitation of total number of granules or number of granules per cell, as well as their intensity or area. So you can see again a lot of intact mitochondria in control samples, and with the samples treated with antimycin A, we see only nuclear mass, but not any intact mitochondria left. This assay could be used as an endpoint or lifestyle real-time assay. It could be used for disease modeling, like oxidative stress or mitochondria damage. So this assay has very good quantitation. So it could be used, granules per cell could be used a parameter to define IC50. So we characterize number of known inhibitor of oxidation, like antimycin A or CCCP, which has IC50s in nanomolar range, and also number of compounds from the library, which are anti-inflammatory or antifungal compounds, which also affect mitochondria, but in micromolar range. Another interesting assay I'm going to describe is autophagy. Autophagy is selective degradation of intracellular targets, which could be misfolded proteins or damaged organelles, and this process is very important for homeostasis of the cells. It's especially important in disease or during starvation, and autophagy may function as survival mechanism to maintain viability during period of stress. For this assay, we use CytoID, autophagy dye from Enzo company, and this dye actually goes into vesicles and turning bright green while when autophagy pathways are activated. Number of drugs being implicated to increase or decrease autophagy. So we characterize several drugs which known for their effect on inducing autophagy. So we've been able to define IC50s for those drugs. And we use granularity analysis, like in case with mitochondria, to characterize and quantitate those effects. Another assay I'm going to describe is phospholipidosis. Phospholipidosis is an excess accumulation of phospholipids in tissue. So it could be caused by certain drugs like antidepressants, cardiac drugs, or cholesterol-lowering agents. Those excess of those agents may accumulate in liposomes and then result in accumulation of phospholipids, which can lead to myeloid bodies formation. So phospholipidosis is an important concern in drug development and could be used as for safety assessment of different drugs. So we have used lipitox reagent from Invitrogen. So in this example, you can see cells treated with propranolol for 48 hours, which resulted in marked increase of phospholipids as well as neutral lipids in a cell. So you can quantitate those changes and visualize those by using lipitox reagent. So we have identified IC50s for number of compounds using granularity model analysis. And so finally, we wanted to validate our assays for high throughput format, and to do so, we use commercially available hepatotoxicity library, medium-sized library from Enzo company. This library contains 240 compounds, which represent different classes of hepatotoxicity, including anti-cancer, anti-inflammatory, neuroleptic, antibiotic, and other types of drugs. Those compounds represent also different mechanisms of hepatotoxicity, as an ALT elevation, steatosis, phospholipidosis, or mitochondrial damage. So we have done this assay using 5 different concentrations up to 100 micromolar concentration. So we have used 2 assays: multi-parametric hepatotoxicity assay, which includes calcium, mitotracker, and HERS, And also we have done short-chain 60 minutes mitochondria potential or oxidative stress assay using JC10. So we read out different output parameters, which include number of calcine-positive cells, mitotracker-positive cells, total cell number, as well as average and total intensity for calcine AM or mitotracker, and also average and total cell area. Also, we have used markers for nuclear characterization and JC10 intensity. On this slide, you can see a representative example of hepatotoxic compounds, like some antifungal or cardiac drugs. And if you use multi-parametric toxicity assessment and look at fold decrease across different parameters, you can get specific profiles for different compounds, which could be used to make an insight into mechanism of action or cluster similar compounds together. So we have used cell count, like for calcine AM, mitotracker, or total cells, JC10 readouts, like number of granule per cell, so total granularity, calcine AM, total area, average area or intensity, and nuclear characterization, like average area or average intensity. So some of those parameters has more dynamic range than others. The one with greatest dynamic range was calcine AM count or total area. So to characterize the hit selection, so we choose cutoff which is greater than 3 standard deviations from diameter controls, and we also require to have a concentration response and more than one parameter affected. So these data are still in the process of analysis, but it shows preliminary predictive value about 70%, which is up to 100 micromolar concentration. So we find that about 2/3 of hits are selected based on count of viable cells or other cell count, and additional 30% of hits selected based on additional readouts like nuclear shape or cell area or intensity or JC10 staining. And also application of different assays and parameters increase number of hits. This assay should be further developed and seems to have reasonable predictive value and good reproducibility and quality. So assay sensitivity for hepatotoxic effects within different compound classes shown on this slide. So you can see that most of toxins show very sensitive in this assay, as well as some anti-diabetic, antifungal, antihistamine, most of anti-cancer, cardiac, or vascular compounds, and as well as neuroleptic compounds. They are very sensitive in this assay. So this general assay model is presented here, suitable for assays in general and specific hepatotoxicity, and also convenient and could be further developed for automated screening environments. Human hepatocytes derived from stem cells offer important advantages compared to other stem cell models. And multi-parametric image analysis greatly increases sensitivity and also provides information about toxicity mechanisms. And this assay has significant predictivity and can improve drug safety by defining toxic effects early in drug development. So I would like to acknowledge scientists from Molecular Devices who helped to collect and analyze this data, James Leslie, Evan Cromwell, and Steve Luke, and also Shannon Acon from Cellular Dynamics, who provided cells and suggestions, as well as our academic collaborators for useful discussions and suggestions. Thank you so much for your attention, and please follow up with the questions.
Thank you very much, Oksana and Vanessa. For those thinking about questions and formulating questions, please go ahead and use the Q&A tab to do that. I will pull up a slide that will remind you how to do that. While we are waiting, there was a question that came in earlier about, this is directed to Oksana, how do you estimate assay quality, Z prime, Z factor? How do you do that?
In our assay, which is actually not high throughput development, but more kind of assay development effort, we usually have number of DMSR controls on our plate, at least 20 wells, and we have some compounds which we kind of expect to have toxicity, and so we have at least 10 different wells with cytotoxic compounds. So then we calculate Z prime using standard deviation and averages between different wells in each particular assay or plate. So using standard formula. So usually those Z primes are pretty good.
Okay. There'll be more questions. They're coming in more rapidly now. This is a question directed at Vanessa. I think there's a background of in hepatocytes that you might want to have cells from with different genetic backgrounds. Is there a way to do assays with cells that derive from different donors, maybe?
Great. So that's a great question, and I should have made a mention to that point in the presentation. The hepatocytes that we're currently manufacturing at commercial scale for customers are derived from a single iPS cell line, and it's the same iPS cell line that we use for our other commercial products for the cardiomyocytes and neurons that we manufacture. However, we have made hepatocytes from iPS cells from a number of different donors, and we are able to differentiate highly pure hepatocytes across multiple donors. We're currently involved in a collaborative project, for example, to make iPS cells and hepatocytes from a number of donors that have had idiosyncratic drug-induced liver injury. And the goal in that project is to essentially model the genotype of those individuals and to develop those hepatocytes into different assays and to evaluate different endpoints to look for the phenotype. In addition, slightly tangent to that, we are doing some projects are moving towards a model of doing co-cultures, for example, with iPS-derived hepatocytes, with iPS-derived Kupffer cells or macrophages to try to better model the in vivo environment that might be contributing to drug-induced liver injury. And that's one benefit of, that's why it's really important to be able to manufacture these cells at very high purity, so that you can take those very high pure populations of cells, mix them together in certain ratios in different formats, which could include different 3D formats, 2D formats, in a very precise and measurable way. And then one more, to add on that one more, we have recently at CDI launched what we call our MyCell services, and this is essentially services that we provide to customers who have access or interest in accessing specific donor genotypes or disease phenotypes. And we're currently embarking on a lot of projects for this to basically make iPS cells from panels of individuals and then to terminally differentiate those into various relevant terminal cell types. So if you do have donor populations that you're interested in modeling, please feel free to contact me to discuss that further. And as part of that service offering, that would include the reprogramming, differentiation, and then if there's any type of genetic engineering of interest, say for example to correct a liver disease gene, for example, or to introduce a specific genotype, we can discuss those capabilities as well.
Oksana, a question for you. In your screen, how many compounds were controls with expected not to have any toxic effects?
In this particular library, which actually we didn't design, we get it from Enzyme Company. So it was 30 non-hepatotoxic controls and also some empty wells across the plate. So I would say like 30 versus other total 240.
Okay. And a little bit about your assay. Can you just describe how the sort of the plating procedure and stuff, so that at how old were the cells by the time you did the assay?
Yes, so I actually described the process in one of the beginning slides. So we plated cells, and then in 48 hours we treated them with changed media to galactose media and added compounds for 72 hours. So after 72 hours, we did staining, which is kind of one step for 60 minutes, and took images immediately the same day. So actually like 5 days total.
Okay. Vanessa, this is a question about how you buy and use the cells. Do you buy them completely differentiated? How many cells do you get? And do you need to? Does the customer need to keep them, and can they keep them and grow them? And on that same note about sort of the workflow of using the cells, what happens when they go through multiple rounds of cryopreservation?
Right. No, those are great questions. So currently, we're providing the cells as fresh cells. Ultimately, our goal is to have these available as a cryopreserved product, similar to our existing cardiomyocyte and neuron and endothelial cell products. So today, when customers receive the cells, they come as aggregates of cells in suspension, so in like a T75 flask. And we have a protocol that walks you through collecting those cells, dissociating and plating those cells. So right now, the workflow is to receive the cells, and then immediately upon receiving the cells, plating them into whatever format you're using for a particular assay. And the cells have been used in a variety of different formats. You can see, from today's presentation, they've been used in 96 to 84 well format, also 24 well format. So I mentioned that ultimately the goal is to have these as cryopreserved cells, and of course we'll do a significant comparison of functionality and responsiveness to compounds compared to the fresh cells before we make those cryopreserved cells available. We've done a little bit of work looking at viral infectivity of cells post-cryo compared to fresh, and those results are pretty comparable. So we're optimistic that the cryo process will still maintain the robustness of the cell function.
And I would like to add that we've been one of the customers working with hepatocytes, and I would say that the protocol is pretty easy to follow, and it doesn't take it takes about several hours to set up culture, including cell plating. So cell viability is very high, and you get very good yield compared to the number of cells you receive. It's about 100,000 of cells, so it was sufficient for multiple steps.
So one general question of Vanessa. Is there any sort of comparison of these cells to in vivo models?
To in vivo models. So we have So, for example, you mean like hepatotoxicity studies in vivo in different models?
Well, there's a question that is actually sure to
okay.
summation.
Sure. Okay. So I think the question is probably the question is probably trying to say are the populations of cells represent growing in the liver, and that's the question. And we don't know the answer to that. It simply means that the cell population is the mixed population of cells that represent different zones in the liver, just based on based on different staining and some morphology of the cells, we suspect that they probably represent different zones within the liver. And then to the other question I thought you were asking first, we have one of our partners, our collaborators at Drug have also done an interesting hepatotoxicity study comparing the isol hepatocyte to results that they obtained in primary hepatocytes from a variety of different species, as well as some in vivo dog data, and they found significant compounds responded similarly in the human isol hepatocytes compared to both the primary hepatocytes of the species as well as the in vivo data. So that may not have been the question that was asked, but I'll answer it anyway.
Thanks. There are quite a number of additional questions. I think with time and people are trying to get into this room, so I wanted to let you know that there's places to learn more from our respective websites. One of the devices is cytoskeleton.com. For cellular dynamics is www.cellulardynamics.com. Also, for those who have meta it's now able to share your questions and with other users. It's network.devices.com/forum. That's a place to have discussions and share protocols. The dynamics and devices will get in tech and that's going to be using a version of this talk that you can come and speak to her directly. And then for medical devices, the show is Icon Analysis in San Francisco. Oksana and I will be there. And we are also having our user meeting there, so we'd love you to come and attend. And if you have time to talk about please let me know. Vanessa can be reached her email v@selective.com. I see there's a number of questions outstanding on understanding more about these cell types. For me, my email is bishop.chandy@molda.com. If you are interested in continuing research or have general questions, please feel free. Earlier on, there was a question about when this material will be made available. There's a website where our webinars are posted. You can right now look at past webinars, and this webinar will be posted in 1 to 2 weeks. Looking forward to talking to you. Please email us directly. Vanessa, do you have anything else to say?
Sounds good. Thank you very much.
Yeah. So those questions are